So good evening, everyone. So we will start our today's session with basics of electrical engineering and design. So last day we have seen we have added the activities for process engineering, mechanical engineering, then civil engineering and piping engineering, and also 3D model. And we have done the interlinkages. Okay, so some of the interlinkages are left because that have dependency with procurement or other disciplines. So now today we will be looking at our balance disciplines, which is electrical and instrumentation. So I will start with electrical engineering first. So basically under electrical engineering deliverables, we have area classification plan as the deliverable, single line diagram, control schematics, substation layout, cable routing, earthing layout, lightning protection layout, lightning and instrumentation plan, cable schedule, interconnection diagram, then design basis, load list, electrical equipment sizing and selection, specification, material of MRs and vendor drawing review. So there are certain studies and calculation also. So there are power system studies which is done in ETAP software. Then we have capacitor sizing calculation, motor voltage drop study, grounding calculation or earthing calculation, cable sizing calculation, lightning calculation, lightning protection calculation. So this is the interface with other discipline. So with process we'll be getting the equipment data sheet, process equipment data sheet, and based on that, the equipment list will be uh, prepared, and then the load list of the mechanical equipment and other equipments will be will be able to know. Then lightning calculation, cable sizing calculation, and lightning protection calculation all will be based on the process equipment data sheet. Based on PNID, we'll be having our control cable selection, motor control schematics. Based on utility flow diagram, we'll decide on the motor rating. Then similarly, the electrical area classification drawing will provide inputs to HAZOP review and study. Then moving to the piping and electrical interface. So basically, based on the plot plan and equipment layout, we'll be having the cable layout, lighting protection calculation, single line diagram, electrical room layouts, cable sizing calculation, all those things. Similarly, based on the size of the electrical substation, electrical room, and cable routing plan, we will further provide input to the overall plot plan where they will be incorporated. It will also provide input to firefighting piping layout based on the location of the electrical room. Then we'll also have HVAC layout. Then based on the civil data, so while doing the geotechnical investigation, we'll be able to quantify the soil resistivity data, and based on that, the grounding calculation will be done, and the size of the conductor which will be used for grounding, all those details will be based on that particular data. Then based on the foundation drawing, paving drawing, and road drawing, the final cable tray layout and the cable routing will be done. Then based on road and drainage drawing, we'll be actually having the street lighting calculation and layout based on the architectural deliverables from civil, like the building basically. So we'll be having the lightning protection calculation and plan, indoor and semi outdoor lightning calculation and plan for the building. Then now electrical engineering deliverables feeding to the civil and structural deliverables. So based on the cable routing plan, the trench foundation drawing will be actually prepared, and also based on the substation layout, electrical room layout, the building, the substation which will be prepared, the structural drawing for and the concrete drawing for that particular substation will be designed. And then based on the electrical equipment general arrangement drawing, we will be preparing the foundation, the concrete foundation for that particular electrical equipment. Similarly, the substation layouts, the electrical room layout, cable routing plan, this will contribute to overall building plan. What will be the size of the where they will be actually placing the electrical room in the building, all those things will be done. Then control and instrumentation deliverable inputs to electrical deliverable. So based on control and control system and electrical interface document, we'll be preparing the electrical control schematic and terminal block diagram. Control cable selection will be there. Power and control cable routing plan will be there. Then based on the UPS load list, you will be actually having the UPS and UPS battery sizing based on which the order will be placed. Based on overall control philosophy, we'll be having the substation electrical room layouts, control cable schedule. Based on the cable block diagram, junction block and instrument cable list, instrument wiring specification, we'll be having the instrument cable routing plan, instrument cable schedule, and instrument wiring notes and detailed drawing. Similarly, with respect to the substation layout, we'll be having the cable block diagram, instrument cable list, IO count, DCS, and SIS document. So to calculate the electrical load, we have to consider the various consumer, which is actually the end consumer. So basically, there are three kind of consumer in plants, oil and gas plants. So the first one is emergency consumer. Okay, so emergency consumer are the those consumer for which there won't be means not even a fraction of second the electricity should switch off. So like the DCS system, ESD system, emergency shutdown system, telecom system. So for that we actually use UPS, batteries and inverter. Then comes the essential consumers. So essential consumers are the plant which are actually next to the emergency consumer. So maybe the power may go for a fraction of second, like 10 second, like switching over from AC to DC in case of power cut. So this includes building HVAC system, motor operated valve, fire water pumps, then heaters to prevent chemical freezing in certain cases. So these are the systems which actually are the essential consumers, and these are feed with emergency diesel generator in case of power break. And then comes the normal consumer. So normal consumers uh, are the one uh, which has no no effect either on the safety or on the safeguard of installation or equipment in case of normal power failure. So this is the basically the process user. So this is a load chart. Uh, Load calculation is done. Load list is prepared based on that. And based on the load list, the equipment, the type of or the size of the equipment is decided basically. So this is a typical load list based on the various electrical equipments or mechanical equipments which will be which will be required for a particular plant. So electrical power balance. So so like if you see here, there are six compressor. So one is four are running, one will be spare, and one is in maintenance. Okay. So we have to maintain the power balance means the load integrated within the plant. So that analysis is done in the power balance system. So there are various calculation which are done, so which includes load flow analysis, short circuit analysis, cable selection, motor starting impact, transient phenomena, protection coordination, and harmonic analysis. So this is basically a load flow analysis. Okay, these are the electrical calculation. This is short circuit analysis. Then cable section is decided also based on the electrical cable sizing calculation is done. So this is the electrical block diagram, which shows like from substation to the field how the power will be supplied. Then this is the single line diagram, electrical single line diagram. It is also called one line diagram. This is switchboard single line diagram. This is electrical distribution diagram. This is also electrical calculation. We have seen this one. Then this is electrical equipment data sheet. So this is for a transformer. So what are the electrical equipment? So there are static equipment, rotary equipment, and miscellaneous equipment. So static equipment involves mainly the power and distribution transformer, high voltage and low voltage switchgear, bus duct, capacitor bank, VFD, VST, then LCI, series reactor, UPS system, battery charger, and battery. The rotary equipment includes generators and motors. And in the miscellaneous category, there are DBs, distribution board cables, LCS. Then we have power socket, light fittings, junction box, earthing, earthing strips, lightning arrestor, earthing bus. So this is a picture of a gas insulated switchgear in the electrical substation. This is the high voltage switchgear. This is a low voltage switchgear. This is basically a network which shows the various uh, voltages across the site required at the site and their interconnection. So this is a switchboard typical diagram. This is the electrical equipment layout. So this is the electrical room, and then you can see these are the panels placed over here. This is the battery room. These are the transformer area. So this is the layout of an electrical room, electrical equipment layout in an electrical room or substation. Then electrical main cable routing diagram. So you can see that this is a trench, and under trench there is a duct bank. Okay, and the duct bank will be carrying the main cable routing the main power supply. Then cable schedule and routing diagram, cable routing diagram. Then we have lighting layouts. So lighting layouts will actually give you where we have to actually place the lights throughout the our facility. Then electrical control systems. So these are the automated systems. So basically these are automated with the help of DCS, and you can see at various section in your plant that what is the voltage, what is the current flowing through, and if there is any breakdown, it will get notified in your screen. So this is also electrical control system. This is for load shedding. So mm, you can see the main power generator is there, and then in case of emergency, it will switch off to the diesel generator and uh, will give uninterrupted power to the systems. Then electrical installation drawing. So it gives you various the diagram that how the electrical equipment will be installed and from where the cable will come. So all those things are mentioned here. This is also a typical electrical installation for a motor. Then electrical control system. So this is actually integrated, means you can see on your screen everything in the dashboard that at which area the power, what is the voltage, what is the how much ampere of current is flowing, if there is any breakdown, all those things will be notified. So this is basically the electrical engineering deliverables workflow. So we have electrical design basis first, then we have the electrical consumer list or the load list, then power balance diagram, then we have the overall single line diagram. After that, we have electrical equipment requirement for package unit like generator, transformer, switch gear, motor, UPS, ACS, and then the data sheet and specification are generated for this equipment. Then we have single line diagram, ACS architects, typical diagram. Then we have the installation drawing like cable routing and cable schedule, typical wiring diagram, standard drawing like power layout, grounding, earthing layout, lighting layout, substation layout is there. And also electrical calculation is there for load flow analysis, short circuit and relay setting. This is also a logical sequence for electrical and its dependency with various discipline. So first will be the electrical design basis, then it will be the design specification, philosophies and data sheet, and then from mechanical and process we'll be having the mechanical equipment data sheets. From there we'll be getting the load list. Then both will lead to single line diagram. And then we also have based on the specification the electrical library setup for 3D modeling and installation specification. So based on the installation specification, electrical installation drawings will be prepared. Then we have overhead line subcontractor. So they will be responsible for erecting the overhead line, electrical line, and that will be work. That will be apply and supply contract. Then we have electrical equipment uh, ordering. Then based on the ordering, the electrical vendor data will come, which will be reviewing basically. And after that, we have bulk MTO. So here we have also have electrical cable trench equipment modeling, and then cable routing, cable trench layout drawing. So based on the load list, we have the cable sizing calculation, and based on the cable sizing calculation, we have the cable schedule, cable drum schedule, cable termination schedule. Based on the equipment sizing, equipment selection will be done. So the various equipment like switchboard, transformer, and they will be actually ordered. And based on the vendor drawing, will be actually having the substation equipment layout. We also have earthing and lighting calculation, and based on that, earthing and lightning and earthing layout drawing will be prepared. So this is the basic workflow of electrical engineering. So this one is also another workflow, the same thing. So here also it shows the same thing, but in a detailed fashion. So that completes our electrical engineering. Now I'll be moving to instrumentation engineering. So under instrumentation, these are the main documents. We have the instrument database, then data sheet, instrument index, then ordering, RFQ, RFP, range, alarm system, then cable schedule, instrument cable schedule, junction box list, IO list, input output list, loop diagram, termination drawing, cause and effect drawing, control narrative, control philosophy, human machine interface graphic details, control system architect, 3D modeling, instrument location drawing, instrument cable tray layout, instrument cable tray loading, HVAC weight loading data, cabinet power requirements, spare part list. So basically, instrument discipline activities includes reviewing the PNIDs and provide input to the process discipline. Then, based on the instrument design basis, okay, where the based on the bid document, the instrument design basis will be prepared. Then, instrument index or instrument list will be getting from our PNIDs. Instrument specification sheet will be prepared, data sheet will be prepared, IO list will be prepared. After that, instrument cable block diagram will be prepared. Field instrument and control system specification will be done. Then we'll be having the procurement engineering, which includes MR, technical bid review, and vendor drawing review. Then instrument cable schedule, JB wiring, instrument loop diagram, instrument logic diagram, instrument control system architecture. So then there will be hookup drawing for instrument installation. Instrument and JV location layout will be junction box location layout will be there. Instrument cable routing and instrument cable tray layout will be there. Material takeoff for instrument, control room layout, and scope of work for electrical installation. So from 3D model, we can extract various drawings like instrument location layout, cable tray layout, JB layout, control room equipment layout, fire and gas detection system layout. So basically from PNID, which is developed by process, we get the instrument list. So this is a PNID. Okay. So instrument index is developed based on the inputs from PNID, which basically lists down the list of instruments required. So this is the instrument list. Then this is input output list for instrument. This is also a input output list. Then this is instrument data sheet. This is also instrument data sheet. So this is actually motor operated valve, or let's say it's a control valve. This is also an instrument data sheet for DP type flow transmitter. This is instrument block diagram, instrument cable routing, instrument cable schedule list, then instrument location diagram. Like you can see, this is a pipe and where we need to place a particular instrument. Like here we have the control valve, and here we will will be having some measuring instrument. Then instrument hookup drawing. Okay, so it gives you the correct position and how you can actually means how the instrument will be placed in the in the process so process pipeline, so that we can easily measure. So basically using the tube and fittings, the instrument will be fit with the help of OLEDs in the pipe. So you can see that in this particular section, the various point instruments are installed. There are uh, dial gauge. So this also section, you can see that uh, this is giving you the that where you are going to actually place the instrument. Then loop diagram. So basically there are two type of loop: open loop and closed loop. So so this is the difference between open loop and closed loop. So in open loop it will be open, there is a no closed loop, and in closed loop you can see that after output it is going to giving a feedback signal again, and it is going to again to the user. So here the error detection system is available. In this case the error detection system is not available, but this one is more costly, this one is less costly. So these are the differences basically. So basically the example of open loop system are like traffic signal, which is a one way, washing machine, bread toaster, and closed loop system is water level control. Like when the level of water reaches a certain, certain level in tank, the motor will stop. It will give signal to the motor to stop. Then automatic electrical iron. So there is a thermostat there, so it will actually control the temperature. It will know that the temperature has now reached to the specified level. So now you can actually switch off the current to make it further hot, the base plate further hot. Similarly, speed control for a DC motor is done using closed loop system. Then serial communication system. So it is used to transmit, data and receive data. So then we have control narrative. So it shows you that what are the what is the architecture of basically the control, how we are controlling the system. So control system includes equipments like PLC, which is programmable logic controller, DCS, distributed control system, safety PLC, or it is also called emergency shutdown system, local controller, remote terminal unit, and fire and gas system, access control system, vibration monitoring, and tank gauging system. So all these things are there. So this is basically a block diagram for a PLC. So it has some sensors, and after sensing it will send signal to the input module, and input module will send further the signal to the CPU. data to the CPU, where it will be actually the logic will be applied, and then based on the logic the output will be generated in the output module, and the data from the output module will go to the actuators, which will actually do the physical work at site. Okay, so like let's say sensors, like example, like there is a there is a uh, sensor that the flow which is actually mm, the like fluid which is flowing in the pipeline. Okay, so it is flowing more than whatever the permissible level is there. So it will give the input to the PLC, and then PLC will give output to the actuator. So the actuator will be, in this case, will be the control valve. So basically the control valve, which is motor operated valve, so that will automatically adjust the valve by rotating in such a way that the flow of fluid in the particular pipe is restricted to the permissible level. So this is also the say another instrument system, which is safety instrument system. So it also based on various inputs, like this is level transmitter, pressure transmitter. It will give it will give input to the logic solver or PLC, and then based on the PLC it will be providing data to the actuator. So you can see these are the motor operated valves. So this is also a block diagram, and you can also, this also has integration with the screen, so that you will be able to see all the parameters over there in your on your screen. So basically at the ground level we have the field instrument, and they are connected using junction box, and after junction box it is connected to marshalling cabinet, then input output rack, and then input output rack feed to system cabinet, which then which are then connected to the systems where you can actually view the processes. So here also it is the same thing. It is showing that field instrument is connected to junction box, and junction box is connected to marshalling cabinet, and which is again connected to system cabinet, and then it is connected to the operator console. So PLC and DCS, PLC is programmable logical control. So it has a single processor. So you can actually connect single PLCs, and whatever the work you want to do. So it is used for small to medium system, few IOs to 1000 IOs, and DCS is a distributed control system. So it has a complicated processor. It has a multiple processor architecture, and multiple communication system is available. So it is used for medium to large system, like 500 IOs to many thousand input output. Then we have a remote terminal unit. It is also similar to PLC. So it has also a capacity of a small to medium system, few IOs to 500 IOs. Then we have SCADA, that is supervisory control and data acquisition system. So it provides actually the human man interface. That is, you will be able to see on your screen the graphics. So SCADA is actually integrated with PLC, RTU and DCS system, which actually helps is to you to see on the operator console how the process is going on. So this is basically human machine interface. So you can see that on your screen it is showing the pressure, the various vessels, and the level indicating the level. It is also indicating the pressure, temperature, all those things. These are the pumps which is actually carrying the fluids, and so you can actually click on you click on the icon, and you can stop a pump, or you can uh, you know uh, close a valve or open a valve as and when required using this SCADA system. Then we have fire and gas system, FNG system. So in fire and gas system, you must have seen this in your office building also, that there is a manual call point, smoke detection, heat detection system is there. This is a fire panel basically. So all the systems are integrated with this one. Then there is a alarm system. There is a hooter system available. Then instrument wiring. So instrument wiring, we have seen that instrument will be connected to the field junction box, and field junction box will be connected to the marshalling cabinet, which will be connected to the system cabinet, and which again the system cabinet will feed to the workstation or control in the control rooms. So you can see this is a typical snip of a control room of a plant. This is also a control room in a plant. Then instrument MTO, so material takeoff. So basically the bulk item like instrument cable tray, instrument cables, earthing strip, instrument junction box, spark plugs, spare plugs, and cable glands, instrument tube fittings, instrument pipe fitting. So all this comes under the instrument MTO. So this is typically an instrument MTO. You can see the unit of measurement like cable trays in running meter and how much running meter it is telling you. Then junction box in number. So all these things are there. Then measuring instrument. So these are pressure transmitters and pressure gauge. We have flow transmitter and flow gauge, temperature transmitter and temperature gauge. Then we have liquid level. So level transmitter is there or level gauge is there. Then density measurement. So you can measure the density or viscosity of the fluid flowing. So basically why we need to what we need to measure basically, so flow in a pipeline, level of a tank, pressure at the suction and discharge of a compressor, temperature of the fluid or hot oil flowing through the pipes. So you can see that this is a typical diagram where you can see that we have level gauge LT, LG, we have level transmitter, and we have the level gauge. So these are the various measuring instrument which is actually attached here. So we have level transmitter, we have level differential pressure transmitter, we have magnetic level gauge, transparent and reflex. So these are the various types of level gauges. Then we have control valves. So you can see over here we have the control valves, instrument junction box. So this is also a diagram of the various instrument attached to a equipment which will be actually giving you the reading. So basically the difference between the gauges and transmitter is that, so in case of gauges, so it will be showing you, in the analog dial. So the person has to go there and see the reading in the analog dial. But in case of transmitter, what it will do, it will be connected with the system using the DCS and PLC, and the operator can see all the pressure and temperature parameter uh, at his computer screen rather than going to the site. So junction box, so you can see that 6 instruments are connected to the junction box, and there are 6 individual lines or cable. And from junction box, only one cable will actually feed to the marshalling cabinet. So you can see over here, it has 6 individual instruments are there, field instrument are there, and the output is in a 6 pair cable. Then we have instrument cable tray for carrying the instrument cables. So these are the instrument cable trays, and this is the logic. So basically, similarly to the uh, electrical discipline, we have the design basis first, then design specification, then we have the process instrument data. So based on that, we have the process data sheet, and the award of the process equipment is being done. Then based on PNID IFA, we have control system block diagram. Based on that, DCS is the DCS specification is decided and DCS is awarded. And then we have the vendor data review. We have the termination drawing based on the vendor data. Yeah, we also have the IO counts from here. We can decide the panel distribution board. specification required, and based on that, the control room layout will be decided based on the size of the equipment. We also have instrument index coming from process, and based on that, we'll be having the instrument index development loop diagram, instrument loop diagram. Based on the installation specification, we'll be having the installation drawings. We have the cable tray, MTOs, instrument location drawings will also be there based on the ordering. Based on that, the cable layouts and cable schedule will be there. So this is basically the instrument workflow. So this completes our presentation for today, and now we'll be moving to P6, where we'll be adding the instrument activities, and we'll be looking at the interlinkages of those activities. So, so I'm putting it side by side for ease in addition of the activities. So we have electrical design basis first, then we have electrical load list, we have single line diagram, main cable routing diagram, equipment design specification and data sheet, lighting calculation, earthing and lightning protection calculation. We have lighting layouts, earthing and lighting protection layout, electrical equipment layout, hazardous area classification, substation layout or electrical room layout, cable sizing calculation, cable schedule and wiring diagram, cable trench layout, cable termination drawing, bulk MTO, and vendor drawing review for the ordered equipment under electrical. Then under instrumentation, we have instrument design basis first. We have instrument index next, IO list, instrument data sheet specification, panel and junction box specification, control system block diagram, DCS specification, instrument location layout, instrument hookup drawing, control room layout, fire and gas layout, instrument cable layout, instrument cable schedule, instrument cable termination drawing, instrument loop diagram, instrument MTO, and instrument VDR. So now we'll be looking at the interlinkages. So, so before interlinkages, we have to put the duration. So let me put the duration. Lighting layout 40 days. This is 30 days. Electrical equipment layout 40 days. Hazardous area classification 20 days. Substation layout is 40 days. Cable sizing calculation is 40 days. Cable schedule 50 days. Trench 50 days. Termination diagram 20 days. Bulk MTO 10 days. And VDR 80 days. Similarly, instrument design basis 5 days, 20 days. IO list is also 20 days. Specification datasheet 30 days. Panel specification 20 days. Control system block diagram 30 days. DCS 20 days. Layout 60 days. Hookup diagram 50 days. Control room layout 80 days. Fire and gas layout 50 days. Cable layout 60 days. Cable schedule 40 days. Cable termination drawing 50 days. Loop diagram 40 days. MTO 10 days. VDR 80 days. So now we'll be doing the interlinkages. So electrical design basis. So it is linked with site visit and data mining and review. Finish to start. And then it is linked with process design basis. Finish to start with 60 days of lag. Electrical load list. So that is dependent on electrical design basis and process equipment list and mechanical equipment list. Then we have single line diagram, which is based on electrical load list. We have main cable routing diagram, which is based on SLD. Equipment design specification and data sheet, which is again based on SLD. Lightning calculation. So for lightning calculation, we have 1450, that is plot plan. We have architectural drawing of civil and electrical design basis. So it will be start to start with plot plan, 30 days lag. With architectural drawing also, it will be start to start, 10 days lag. And it will be finished to start with the electrical design basis. Then earthing and lightning protection. So it is based on similarly the plot plan. So we have plot plan, start to start, 30 days. We have design basis and geotechnical survey. Then lightning layout. So lightning layout is based on design basis and lightning calculation. Then earthing and lightning protection, which is based on earthing and lightning protection calculation. Electrical equipment layout, which is based on plot plan. Then equipment design, specification and equipment data sheet. And we have vendor drawing. So with vendor drawing, it is 20 days of lag. With plot plan, it is 30 days. And with data sheet and specification, it is finished to start. Then hazardous area classification. This is linked with design basis and process equipment list. Then we have substation layout, which is based on electrical equipment layout and hazardous area classification. We have cable sizing calculation, which is based on electrical load list. Then single line diagram and main cable routing diagram. So with single line diagram, it is start to start with 20 days of lag. Then the next one is cable schedule and wiring diagram. So it is linked with cable sizing calculation. Then we have cable trench layout. It is linked with cable schedule and wiring diagram and main cable routing drawing. We have cable termination, which is cable schedule and wiring diagram and cable trench layout. Bulk MTO, which is linked with lighting layout, earthing and lighting protection layout. Then we have cable schedule and wiring diagram, cable trench layout, cable termination diagram. Then VDR, so it is linked with procurement. So we will highlight it in yellow. We'll be doing the linkage once we have the ordering done. And similarly for instrument, we have site visit and data mining, then process design basis, finish to start, 60 days of lag, instrument index, it is process data sheet, instrument data sheet, and PNID IFR, start to start, 5 days of lag, and instrument design basis. Then we have IO list. which is based on instrument index, instrument data sheet. So this is based on instrument index, panel and JB specification. This is based on IO list, control system block diagram. So this is based on plot plan, start to start, 20 days of lag. We have PNID IFR and instrument design basis, DCS. It is based on control system block diagram, instrument location layout. It is based on IO list, data sheet, and VDR. So with VDR, it is 20 days of lag. Then hookup diagram, so which is based on instrument index, instrument data sheet and specification, and piping material class. Then control room layout, that is based on instrument data sheets and PNID IFD. And fire and gas system layout, so that is based on plot plan, start to start, 60 days of lag. Then PNID IFR, no, PNID IFR will not be there. So for FNG layout, we have plot plan, and then we have instrument design basis and instrument index. Instrument cable layout, we have instrument location layout, instrument cable schedule, we have instrument hookup drawing, and instrument cable layout. Cable termination drawing, that is based on location layout, hookup drawing, and control room layout. Loop diagram, that is based on instrument index, hookup drawing, and cable schedule. MTO, that is based on instrument index, sorry, instrument data sheet, instrument hookup diagram, and cable schedule. And vendor drawing review. So vendor drawing review will be based on ordering. So we'll be linking it once we have done the ordering of the equipments. So this completes our linkages for instrument and electrical discipline except for VDR. So VDR will be linking after the ordering of equipment. So now we have populated the electrical engineering activities and instrument engineering activities. So next we'll be moving to procurement. So we'll be adding the various equipments and the bulk item which are required to be procured for this LNG plant. So we'll be having a small presentation on this LNG plant procurement items on Monday after the doubt session. Uh, and then we'll be adding the procurement items maybe on, if possible, on Monday, some items, and on Tuesday, the balance item. So now if anyone has any doubt with respect to today's session, please let me know. If anyone has any doubt, please post in the chat box, or you can unmute yourself and ask. Yeah, anyone has any doubt, or shall we close the session for today? It seems no one has any doubt with respect to today's session. So Taniska, you can close the session for today, and we will meet on Monday.
Awesome.
Yeah,
Thank you so much, sir. Thank you, dear learners. If you don't have any doubt, conclude the session.
thank you. Good night.